All right, hey everybody, we're going to talk about, I didn't label this, whoops. This is 15.1 to about 15.6 in the book. We're going to talk about equilibrium, dynamic equilibrium, essentially dynamic meaning changing and moving equilibrium. So I start by saying I want to do a demo. We'll do a demo in class with people, but let's see. Let's do this. Okay, so let's say I have a reaction, which is, I don't know, let's do 2A in equilibrium with 4B. Okay, so let's say this is my A stuff. I got two of them, 2 A's. These are my 4 B's. Okay, what equilibrium means is not that you have equal amounts on either side. It's that they're moving at the same rate. They're in equilibrium. The rate going this way to the right is the same as the rate going to the left. So let me give you an example of that. Let's say every 4 seconds, we're going to move things around. And we'll just constantly keep it at every 4 seconds because that would be the same rate, right? So like 1, 2, 3, 4. Let's go over there. That goes there. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So hopefully you understand, it just means the same rate. The same speed that stuff's moving this way is the same speed that stuff is moving that way, and it doesn't necessarily mean that they're equal. I could have had 100 of these and however many of these. The ratios, though, would had to have been relatively the same, but it doesn't matter how much you have on either side. It just happens that has to be the reaction speed this way is the same as the speed going in the opposite direction. So that's a demo I wanted to do with y'all tomorrow or whenever you're watching this. Okay, so we're going to be talking about the equilibrium constant. What the equilibrium constant does is it tells us the concentrations that are present when equilibrium occurs, when that rate forward is the same as a reverse. We generally express this with what we call the equilibrium expression. So this would be called the equilibrium expression. All right, so if we have some kind of A, the little ones being the coefficients, and the big letters actually representing the compounds or atoms that are reacting, we're going to put it in something like this. The important thing is to recognize that we're always putting products over reactants. So we take the products here and raise them to the power of their coefficients, and same down here. So let's practice real quick. It's easier to actually do than it is to look at, I think. All right, so we have this reaction, and we want to write an equilibrium expression. Well, we're going to start with K. And again, we know it's always going to be products over reactants. So let's look at the products. We have NO2. And it has a coefficient of 4. So we'll put that 4 up there. Times O2. And it has a coefficient of 1, so we don't need to write anything. All over our reactants. And that has a coefficient of 2. So this would be what we call the equilibrium expression. Sorry for those of you who are OCD or organized, that must really irk you. It irked me too, to have it so off. But this would be the equilibrium expression, and your homework asks a lot about that. All right, so I was going to have you do one on your own here. So you can pause the video or not, but H2 plus I2 yielding 2HI. So our equilibrium expression for this, always products over reactants, would be this HI. And it happens to have a 2 there over H2, the 1 power times I2. Erase the 1 as well. All right, so that would be the equilibrium expression. Now I included this table, and this table might be a little bit premature, but we're going to get into it today. I thought it was interesting because it kind of gives us an idea of what happens at equilibrium. don't forget that when we're talking about this stuff, it's not some abstract thing. You could actually go get H2 gas and iodide gas, and you can mix them together, and you get this hydrogen monoiodide. You can or iodic acid if it happens to be aqueous, but yeah, it's not. So these are actual real things you can do. You can take some of this, you can take some of that, you can mix them together, and you get that. Like, it's pretty cool. So this gives us real world examples of what you might start with, initial concentrations. So let's say in some kind of reaction vessel, it's a gas, so it'll have to be like a closed flask or something. You're reacting H2 and I2. Now you start in this one with 0.5 mole per liter, and this one's 0.5 mole per liter, and you don't have any HI. But that's okay, because these things are going to react and move this way until they establish equilibrium, where the rate going this way is the same as the rate going that way. That happens to be when the concentrations are these things. But the important thought here is that if you put those into the equilibrium expression, so if the concentration of H2 is 0.11 and I2 is 0.11 and HI is 0.78, if you put them into those concentrations into the equilibrium expression that you derived up here, you will get the number 50. Even if you start with absolutely no H2 and no I2, and you only add HI, then the reaction goes this way until you have an equilibrium. Until you've established an equilibrium and they're super happy. And then the exact same thing happens. The concentrations might be different, but the rate relationship in this equilibrium expression always ends up to be the same ratio. They always end up to be 50. No matter how much initial stuff you start with, it always finds a way to balance itself and go to equilibrium where those rates forward are equal to the rates reverse. And that's pretty cool about equilibrium. That's one thing that I think is fascinating. That doesn't matter how much you add, you'll always end up with this when you have reactions that are at equilibrium. Another something that's noteworthy, we're not going to include solids or liquids in equilibrium expressions. That's because they don't have concentrations. Like if you take a big block of lead and you put it in water, it's not dissolving in the water, so there is no concentration. You don't actually have anything that's aqueous, or if it's not, you could have a gas be mole per liter, and we'll talk about that here in a little bit. But overall, if you got a solid, you don't use it. So if we went to write this equilibrium expression, we only use the gas divided by that one, and this is not used in the equilibrium expression. All right, but what does K mean though? All right, to figure out what K means, we need to kind of go back to, let me grab some more paper. We need to go back to elementary math. Okay, so we're going to take a step back. I'm going to keep the top number the same, the numerator the same, and I'm going to increase the denominator of this series of numbers that we're just going to pretend we know nothing about what's going on, because you probably don't actually at this point, about why I'm writing these. Okay, so 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, etc. As I go from left to right, as I increase the denominator, what happened to the value of the overall number? It got smaller, right? This was 1, this was 0.35, or this is 0.5, this is 0.33, this is 0.25, this is 0.2, etc. It got smaller. So as this bottom number gets bigger, the overall value gets smaller, okay? If I were to do the opposite, 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, 6 over 1, etc. As this number increases, we're getting bigger. But in this case, we got smaller. So how big the numerator or denominator is changes the value of the number, right? So if you have a big denominator, you're going to have a small number. If you have a big numerator, you're going to have a big number. All right, let's remember that K was products over reactants, right? So if you have a lot of reactants, that means this bottom number is going to be bigger, right? The reactant number is going to be bigger. And so if you have lots of reactants and this number is bigger, that means your K will be small. Generally, we're going to say it's less than 1. By the opposite idea, if we have a high number of products, so your reaction goes and you make a lot of products, that means the numerator is getting bigger. And your K is going to be big, greater than 1. Okay? So if you have the bottom number is really big, your K is going to be small. If the top number is really big, your K is going to be big. Let's relate that here to this. All right, in this reaction, our K is 1.9 times 10 to the 19. Is that big or small? Hopefully you said it's big, but just in case we've missed this lesson, I don't know, I lost count. 1, 2, 3, 4, 5, 6. Boom. It is that big. That's a big stinking number, right? So K is big. What that tells us is that there are more products. Remember, K equals products over reactants. What it tells us is there's more products, meaning this is favored. It wants to make a lot of that. That's what K essentially tells us. If K is really big, it tells us, hey, it really likes that HBr. Okay? By the opposite idea, if we have I think that's right. Don't count it. I think there's 30 zeros. But if you have this number, which is what that is, what that tells us is that it really likes reactants. And the reactants are favored. Remember, once again, that's because K equals products over reactants. I hope you'll agree this is a small number. In order for that to be small, the reactants must be big. And that's why it's telling you that those are favored. Okay. So this just kind of sums up the same thing. If K is less than 1, then the reactants are favored. In other words, the reverse going this way, that way is favored. And the reaction doesn't proceed very far. If K is about equal to 1, it's happy to be either way. And if K is greater than 1, then it means it's going this way. And it'll keep proceeding to the right. One interesting thing is most reactions are theoretically in equilibrium and theoretically reversible, at least. And I just think that's kind of a cool thought. Okay, so expressing equilibrium in terms of pressure. So this is something that I could get really into, or I could not. I've decided to err on the side of not, because it's not something you come across too terribly much. Partial pressures, this should be from, I think, chapter 10 in your book from Gen Chem 1. If you'd like a review on partial pressures, I'll actually post it just so you have an idea of what they are. But equilibrium can be expressed in two ways. And concentration, that's what that C stands for. And if you remember, concentration is big M, which is mole per liter. So that's all these brackets mean that we're talking about concentration in mole per liter. And P means pressure. where this is the partial pressure. And we usually like to stick an ATM. Okay, so it could be either way. If you have a gas, it depends what information you're given. Oftentimes you're given moles per liter, but sometimes you might be given the partial pressure. The concept is exactly the same. You would still set it up exactly the same, except you'd want to indicate that you're solving for Kp instead of Kc and vice versa. They are related, and they're related via pretty standard set of numbers. So I'm going to briefly talk about that, and we will solve for one problem. So let's see how to go about this. I think the best way is to remember what concentration is. Okay, so let's say you have the concentration of something, A. What we're talking about, right, is the moles of A over the liters of solution. Okay. Another way that we would express that is with N. Hopefully you've seen N used I can't think of the name, as a variable for moles. And L is the unit of V, V being volume. So this is just a way of expressing it in terms of using a variable, Na over V. Okay. Pressure, the times we've talked about pressure have been via this relationship with the ideal gas law, where PV equals nRT, or the pressure of one particular compound times the volume, whatever container it's in, is equal to the moles of that particular compound times RT. Okay, so these two concepts will allow us to kind of derive the relationship between Kc and Kp. We know that the concentration of A is this over that, okay? And we can actually solve here for that part. So I could take PA, and I'm going to divide both sides by V, and that equals N sub A over V times RT, right? So I just moved V over here, divided each side by V, and that gave me N sub A over V, which we should recognize it's up here. N sub A over V also equaled the concentration of A. That's by definition what the concentration is. It's moles over liters. So we can say all right, so this was just a brief way to prove to you that pressure and concentration are related via just two variables, R, which isn't even a variable, it's a constant, and T, the temperature. Okay, so I could go on to prove the rest of it, but I prefer to use my time in an alternate way and just show you that that same concept here relates down here. Kp is equal to Kc times RT to the change in N, where the change in N is the change in the number of mole of gas. In other words, number of gas mole on the product side minus, let me write this better. So delta N equals the number of gas moles on the product side minus the number of gas mole on the reactant. Remember, we're always doing final minus initial. So that's how this equation goes. Let's use it so we can see if it makes sense. I'm sorry for those of you on the internet who may be not able to read this. This is pretty light, small font. Let me zoom in a little bit. Okay, so it says nitrogen monoxide, a pollutant in automobile exhaust, is oxidized to nitrogen dioxide in the atmosphere according to the equation. So we got 2 nitrogen monoxide plus oxygen into nitrogen dioxide, and it tells us our Kp at 25 degrees Celsius. It wants to know the Kc. Well, the equation we have is Kp equals Kc. There's that factor R10 to the delta N. So this is the equation we're going to be using. We know Kp, it's right there. we're solving for Kc. R, we know that's the gas constant. T, we also know it's 25 degrees Celsius, but remember, we want to add 273 to that to put it into Kelvin. And then the change in moles of gas. That's the one thing that I want to spend a little bit of time here on. I told you that it's going to be the number of moles of gas on the product side minus the number of moles of gas on the reactant side. By number of moles, all I mean is we add up the total amount of moles based on their coefficients on each side. So delta N here equals the total number of moles on the products. Minus the mole of gas on the reactants. The total number of moles of gas on the product side is 2, because this is a gas and there's a coefficient of 2. Minus, these are both gases, there's a coefficient of 2 and there's a coefficient of 1. 2 plus 1 is 3. So there's 2 moles of gas on the product side and there's 3 moles of gas on the reactant side. So delta N equals 2 minus 3, in other words, negative 1. That's how we're going to solve for our moles of gas. All right, now we can kind of just plug and chug. We know our Kp is that, so I'm just going to start plugging things in. Our Kp is that, our Kc we don't know. This is 0.082, I think your book has to use 206 liters times ATM over mole times Kelvin. And then we know our T is that, and we know this is negative 1 now. So we can just plug everything in. Our Kp is 2.2 times 10 to the 12. I'm setting that equal to Kc times 0.0821 liters ATM over mole Kelvin. I'm going to zoom out a little bit. Times, and I should put this in bigger parentheses, times our temperature, 298 K, raised to the negative 1 power. So this times this, all raised to the negative 1 power. All right, let's break this down to make sure we're comfortable with this calculation. So I'm going to start with this part. We have 0.08206, oh my bad, let's just have it, 206 times 298. I'm going to hit enter, and then you just raise it, little hat, to the negative 1. And hit enter. So this gives me a total of 0.040893 times my Kc is equal to 2.2 times 10 to the negative, or 10 to the positive 12. Okay, so I can just do 2.2 times 10 to the 12. I could divide it by my last answer by moving up, or just say divide it by 0.040893. And I get an answer of, I'm going to compare it and make sure I got the same number, of 5.4 times 10 to the 13. And that would be your answer. So they're close. Remember, Kp and Kc should be relatively close depending on the number of moles of gas there are. But yeah, they're within an order, they're about an order of magnitude apart, and that's pretty great. So, all right, now let's move on. Let's go ahead and use K. So very rarely will you be asked to use, to convert between Kc and Kp. I think this is just more important for you to realize that they're not equivalent, but they do work very similarly. And they are related by something that if you solve for Kp and you don't know Kc, you can figure it out, and vice versa. All right, so let's use K. First, let's go ahead and find the value of K in this particular problem. So it says at a particular temperature and at equilibrium, H2 equals 0.11, I2 equals 0.11, and HI equals 0.78 for this reaction. We already did a K for that reaction. We said it was HI squared over H2 I2. and we want to know the value of K. The beautiful thing is it tells us that this is all at equilibrium, so all you need to do is plug in the numbers at equilibrium and solve. Our HI, it tells us is 0.78, and we have to square it because that's what that coefficient tells us. I'm going to divide that by 0.11 and a 0.11. That's because the H2 was 0.11 and the I2 was 0.11. Calculate this. 0.78 squared divided by 0.11 divided by 0.11. Various ways you could do this. And you get an answer of 50.28 or just 50. You could also put that as 5.0 times 10 to the 1 if you don't like the decimal place after the 0 because it does look kind of funky. Moving on, ice tables, word. I love ice tables. Hey. This is when you know you're in Gen Chem 2. Okay, so for the following reaction, so you have some A going to some 2B. It wants to know K. Well, you know K, the equilibrium expression would be B squared over A. And we could have used partial pressures of each, but I see that the next part gives us mole per liter, and so I'm going to use the brackets to indicate mole per liter. All right, so this is what our K would be equal to. It says A is initially 1 mole per liter, and B is initially 0 mole per liter. And it says to get to equilibrium, A, and I believe that should be a bracket right there, is reduced by 0.25 mole per liter. Okay? It says use an ice table to determine K. Whoa. So let's go ahead and go through what an ice table is. Generally, when you're doing an ice table, you start by writing the your equilibrium reaction. Next, you're going to write the word ice. I stands for your initial concentration. C stands for your change in concentration. And E is your equilibrium concentration. I generally put a line before E because you're going to sum things up to get E. Okay, so our initial concentration of A was 1.00. It said B was initially 0.00. Although if it doesn't mention something, we automatically know that it was 0. So in future problems we're going to come across, it won't mention the other products or the other reactants, so we'll just know that they weren't initially there. So we'll put a 0. Now it says change. Well, it tells us to get to equilibrium, A was reduced by 0.25 mole per liter. So it started at 1, it was reduced by 0.25. So we lost 0.25. My question to you though, and this is where change becomes pretty important, if we lost, my phone died. All right, so if we lost one of these, we had to have gained 2 of those, right? So if we lost 0.25 of these, that means we had to have gained 2 times 0.25 of those. I hope that makes sense. I'm going to say it again. For every one of these that we lose, we have to gain 2 of those. So for every A we lose, we have to gain 2 B's. Over here, so if we lost 0.25 of A, we had to have gained 2 times 0.25 of B. And then equilibrium tends to be relatively straightforward. That's where we just sum everything up. It's the initial plus the change. This getting negatives signs right ends up being kind of important on this. So make sure you read the question and think about things. It said reduced by 0.25, and that's how I knew it lost 0.25. So this would be 0.75 mole per liter, and 2 times 0.25 is 0.50. In other words, 0.50 mole per liter. So these are our concentrations at equilibrium in this example problem. And if I'm solving for K, remember our initial equilibrium expression was just based on what the reaction showed us, products over reactants. Now we just plug and chug. 0.50 squared divided by 0.75. So 0.50 squared divided by 0.75, and I get an answer of 0.33 repeating, and that would be our K. What does that K tell us, out of curiosity? Remember, it's a smaller K, it's less than 1, it's kind of close to 1, so it's not too crazy, but it does tell us if it's less than 1, that reactants are favored just a little bit more. But this A is favored a little more than the B. All right, all we have left is a couple example problems to be precise. These are really fun. I hope you like them. Ice tables are pretty cool. Okay, so anytime you're given something initial or see a change and it's asking for the equilibrium constant, or it gives you an equilibrium constant, it's asking for some unknown concentration, we're probably going to use ice tables. So it says, consider this following reaction. At 780 Celsius, initially, it contained 0.50 mole per liter of carbon dioxide and 1 mole per liter of this hydrogen. And it's at an equilibrium, the concentration is 0.1. The CO concentration specifically is 0.15. What is the value of equilibrium constant? That's a lot of words, so what we do is build an ice table and try to put everything where it goes. So we got CO plus 2H2 in equilibrium with methanol here. Another thing that I like to do, just to get it out of the way so I don't make mistakes, is write the equilibrium expression. I know that that's going to be my products over my reactants. Okay, because you're probably going to come back to that at some point in time. All right, so we've got our reaction, we've got our ice. Let's fill everything in. Okay, it says initially it contained 0.500 mole per liter of this carbon monoxide. Perfect. That's easy. It uses the word initial, so we know it's going to go there. And 1.00 mole per liter of H2. Cool. It didn't say anything about the initial concentration of CH3OH, of this methanol. And so, like we said in the last problem, if it doesn't say anything, we're just going to assume it's 0. They didn't add any actual methanol to it. They just mixed that and that. It said at equilibrium, the CO concentration is 0.15, meaning down here, it had to be 0.15. Well, remember, in order to get the equilibrium, we have to add these two lines. So this is like an algebra problem. 0.5 plus what equals 0.15. That what has to be negative 0.35. Or you could have solved it by saying 0.5 minus 0.15 is 0.35. So I knew I had to have lost 0.35 in order to get that. That sets up everything. If you know the change, you can figure out a lot of stuff, because if for every one of these, we have to have lost 2 of those too, right? So if this is negative 0.35, this has to be 2 times negative 0.35. In other words, 0.70. So if we lost one of those, we had to have lost 2 times that amount over here. And guess what we had to do over here? We had to gain 1 times that amount. So if we lost 0.35 here, we had to gain 0.35 here. That number only changes, we only put a 2 here because of the coefficient 2. And now we can do the rest here. So this, by the way, would equal negative 0.70. And when we add everything up, 1 minus 0.70 is 0.30, and over here, 0.35. Those are our equilibrium concentrations. When the rates are happy and going their appropriate direction, that's when we're able to then plug and chug stuff into this equation. All right, so let's do that. Our methanol here is 0.35 over our CO, which is 0.15, times our 0.30, and don't forget to square it. And let's set that up. 0.35 divided by 0.15, and then divided by 0.3 squared. And that gives me an answer of 25.9, or 26.1 What does that mean? Products or reactants favored. That means that the products are favored. So the methanol is favored in this reaction. Methanol is preferred. All right, let's keep it going. Do this last one here. Okay, it says consider the following reaction. Same kind of concept. 2CH4 yielding C2H2 plus 3H2. And then it gives us all this information, and it says initially contains something. When I see the word initial, I see equilibrium, I think ice table. And so let's do it. We have 2CH4 yielding C2H2 plus 3H2. And we're going to do our ice. All right, I also, like I said, like to get the equilibrium equation out of the way, expression. So this is going to be C2H2, H2 cubed, all over CH4 squared. All right, let's fill this in. It says it contains initially 0.115, the CH4. At equilibrium, the mixture contains 0.350, or 0.035, my bad, of this C2H2. That's all the information we have, but that's actually all the information we need. Because we know it initially contained only this, that means that this had to have been 0, and this had to have been 0. If it doesn't give us the information and tell us what we initially had, or ask for what we initially had, it means there was nothing initially there. All right, so in order to go from here to here, our change had to have been plus 0.035. There's no other option. If we gain 0.035 here, we had to have gained 3 times that amount, or 0.105. Again, that's just, I just took 3 times 0.035. So that means here at equilibrium, this is 0.105. All right, now the change here. If we gain 0.035 here, how much did we have to lose there? Well, we had to have lost 2 times that 0.035, or negative 0.070. So if we have the 0.115 minus this 0.070, we get 0.045. So it's pretty cool that we only started with this, and we were able to figure all of the rest of it out. Let's go ahead and plug it in because it asks for the value of the equilibrium constant. We have 0.035. Our H2 was 0.105, and that was cubed, divided by 0.045, which happens to be squared. Let's do this. 0.035 times 0.105 cubed divided by 0.045 squared. And I get an answer of 0.020. What's favored? The reactants must be favored. In other words, the reverse reaction is slightly favored because it's less than 1. I think that's it. All right, happy equilibrium learning, and good luck on ice tables. They're pretty rad, right? Talk to you guys in class. Bye.